When the Second World War ended, Germany's relationship with aviation did not disappear. It was forcibly interrupted, dismantled, and then carefully reconstructed under close Allied supervision. German engineers, many of whom had worked on some of the most advanced aircraft designs of the 1940s, found themselves reassessing their assumptions in a new strategic environment. The early Cold War did not simply present Germany with a political realignment, it imposed a technical reckoning. The United States, now the dominant air power within NATO, introduced aerospace systems that redefined scale, endurance, and operational doctrine in ways that German specialists had not previously encountered. By the early 1950s, as West Germany began its gradual reintegration into Western defense structures, German engineers and military analysts were exposed to American aircraft not as wartime adversaries, but as Allied systems intended for joint operation. This shift fundamentally altered the nature of observation. Instead of reverse engineering wreckage or relying on intelligence fragments, German specialists now had access to live demonstrations, technical briefings, and operational exercises involving U.S. aircraft. What they encountered challenged long-held beliefs about efficiency, design philosophy, and the relationship between engineering and logistics. One of the earliest and most consequential points of comparison involved strategic bombing doctrine. German wartime aviation had emphasized precision, speed, and tactical effectiveness within relatively constrained operational ranges. American aircraft, by contrast, were built around endurance and redundancy. The B-29 Superfortress, and later the B-36 Peacemaker, represented a category of aircraft that prioritized sustained global reach over minimalism. For German aerospace analysts, this was not simply a matter of size. It reflected a different conception of air power itself. American aircraft were designed to operate continuously across vast distances, supported by an industrial and logistical framework that assumed prolonged engagement rather than decisive singular strikes. This divergence became even more apparent with the introduction of the B-52. German engineers studying the aircraft through NATO channels noted its longevity as a design anomaly. The B-52 was not optimized for speed or elegance, yet its structural resilience, modularity, and adaptability defied conventional expectations. Reports from German technical observers highlighted the aircraft's ability to incorporate successive generations of avionics, weapon systems, and electronic countermeasures without fundamental redesign. This capacity for evolution, rather than obsolescence, forced a reassessment of what constituted successful aerospace engineering in the post-war era. Beyond the aircraft themselves, German specialists increasingly focused on the systems surrounding American air power. Aircraft were only one component of a broader operational ecosystem that included maintenance infrastructure, training pipelines, supply chains, and command integration. American aerospace dominance appeared less dependent on any single breakthrough than on the coherence of these interconnected elements. For engineers trained in environments where technical excellence was often isolated from organizational context, this systemic integration was striking. It suggested that technological superiority was being sustained, not by isolated genius, but by institutional continuity. As German engineers continued their exposure to American aerospace programs throughout the 1950s and early 1960s, attention increasingly shifted from individual aircraft to production philosophy. Pre-war and wartime German aviation had achieved remarkable feats through precision craftsmanship and experimental innovation, but often at the expense of scalability. American aircraft programs, by contrast, appeared to be conceived with mass production, maintenance standardization, and lifecycle longevity as foundational principles rather than afterthoughts. This distinction carried significant implications for sustained air power during a prolonged geopolitical rivalry. The F-86 Sabre provided an early illustration of this difference. German analysts studying the aircraft in NATO contexts recognized its aerodynamic sophistication, particularly in transonic performance. Yet what stood out was not merely the aircraft's flight characteristics, but the industrial ecosystem that supported it. The Sabre was produced in large numbers, deployed across multiple Allied air forces, and maintained through standardized procedures that reduced dependency on specialized artisanal labor. This approach contrasted sharply with earlier German experiences, where cutting-edge designs often demanded bespoke solutions that limited operational flexibility. The pattern continued with the F-4 Phantom II, an aircraft that would become emblematic of American aerospace philosophy. German engineers and pilots who later operated the Phantom within the Bundeswehr noted its apparent contradictions. The aircraft was heavy, visually unrefined, and mechanically complex, yet it delivered consistent performance across a wide range of missions, climates, and operational conditions. More importantly, it functioned as part of an integrated system that included radar networks, early warning platforms, and coordinated command structures. Its effectiveness could not be assessed in isolation, a fact that repeatedly appeared in German technical evaluations. American aerospace programs also demonstrated a tolerance for incremental imperfection that differed from traditional German design culture. Rather than pursuing flawless initial specifications, U.S. aircraft were frequently introduced with the expectation of continuous improvement through upgrades and retrofits. German engineers recognized that this approach reduced development bottlenecks and allowed operational experience to directly inform subsequent iterations. The result was a feedback loop between deployment and design that accelerated adaptation. In a Cold War context defined by uncertainty and rapid technological change, this flexibility proved strategically advantageous. By the early 1960s, German assessments increasingly acknowledged that American aerospace superiority could not be reduced to engine performance, airframe design, or avionics alone. It rested on an industrial and organizational framework capable of sustaining complexity over time. Aircraft were treated not as static products, but as evolving platforms embedded within a broader strategic system. This realization marked a significant shift in perspective. The question was no longer whether German engineers could match American aircraft in isolated metrics, but whether any single design culture could replicate an ecosystem built for scale, adaptation, and endurance. These early encounters laid the groundwork for a deeper understanding that would continue to unfold throughout the Cold War. What began as technical comparison gradually evolved into a broader reassessment of how air power was conceived, produced, and sustained. For German specialists, the exposure to American aerospace systems was not merely informative, it was transformative. It revealed that technological leadership, in the Cold War environment, was less about achieving perfection and more about maintaining momentum. As the Cold War intensified, German aerospace specialists were confronted with a category of American aircraft that challenged not only design expectations, but the very assumptions underlying air defense. Strategic reconnaissance platforms forced a reconsideration of interception as a feasible objective rather than a guaranteed capability. This shift was not theoretical. It was driven by concrete American programs whose operational parameters exceeded existing European and Soviet interception frameworks. For German analysts trained in air defense doctrine, this marked a turning point. Early exposure to the U-2 reconnaissance aircraft already suggested that altitude itself could function as a defensive system. German air defense studies from the late 1950s noted that the U-2 operated beyond the effective ceiling of most contemporary interceptors, rendering traditional engagement models obsolete. While the aircraft was eventually challenged through surface-to-air missile development, its operational success underscored a broader American willingness to exploit physical domains others had not fully prioritized. Altitude, endurance, and intelligence integration were treated as interdependent variables rather than isolated characteristics. This conceptual shift became far more pronounced with the emergence of the SR-71 Blackbird program. German aerospace analysts encountered the aircraft not as an adversarial threat, but as a technological reference point within NATO intelligence briefings and Allied assessments. The SR-71 was not evaluated as a conventional aircraft. It was described as a system operating at the intersection of aerodynamics, materials, science, propulsion, and intelligence doctrine. Its sustained flight at Mach 3 and extreme altitudes placed it outside the engagement. envelope of existing interceptor aircraft and missile systems for much of its operational life. German technical assessments emphasized that the Senior 71's significance lay not in any single breakthrough, but in the coordination of multiple advanced domains. Titanium airframes capable of withstanding thermal stress, specialized fuel formulations, adaptive flight profiles, and real-time intelligence integration combined to create an aircraft that redefined survivability. Interception, in this context, became a theoretical exercise rather than an operational certainty. German analysts noted that even when detection occurred, response timelines were insufficient to enable effective engagement. This reality challenged decades of air defense planning. What unsettled German specialists most was not merely the aircraft's performance, but the doctrinal confidence behind it. The SR-71 was deployed with the assumption that its operational parameters rendered it functionally immune to interception under prevailing conditions. This assumption proved largely correct for years. German air defense studies began to reflect a growing acknowledgement that certain American aerospace capabilities operated beyond the reach of traditional countermeasures. The implications extended beyond reconnaissance. They suggested a future in which dominance would be defined by system integration, rather than numerical parity. The presence of American strategic reconnaissance platforms forced German military planners to confront uncomfortable questions about the limits of defensive systems. Traditional models of air defense relied on layered interception, detection, tracking, engagement, and neutralization. American aerospace developments disrupted this sequence by compressing timelines and expanding operational envelopes. German analysts increasingly recognized that interception was no longer a given outcome, but a contingent possibility dependent on technological synchronization. German evaluations of NATO air defense exercises revealed the growing gap between detection capability and interception feasibility. Radar systems could often identify high-altitude, high-speed targets, yet the time required to scramble interceptors or activate missile systems exceeded the window of opportunity. This discrepancy highlighted a structural vulnerability that could not be resolved through incremental upgrades alone. German aerospace specialists concluded that the challenge was systemic rather than tactical. Defensive architectures designed around predictable engagement profiles were ill-suited for platforms operating at the extremes of speed and altitude. American doctrine appeared to embrace this asymmetry deliberately, rather than pursuing absolute invisibility. Reconnaissance platforms prioritized operational parameters that overwhelmed defensive response mechanisms. German analysts noted that this approach reduced reliance on countermeasure complexity by exploiting physical constraints inherent in interception. Speed, altitude, and range functioned as defensive assets. This reframing of survivability resonated deeply within German technical circles, where survivability had traditionally been achieved through maneuverability or defensive armament. The implications extended into broader aerospace planning. German engineers began to reassess the relationship between aircraft design and strategic purpose. American platforms were not optimized for dogfighting or aesthetic efficiency. They were engineered to fulfill specific operational roles within an integrated intelligence ecosystem. Reconnaissance data flowed directly into strategic planning, enabling rapid decision-making at the highest levels. This seamless integration between aircraft and intelligence infrastructure distinguished American aerospace systems from more compartmentalized European models. By the mid-1960s, German aerospace discourse increasingly acknowledged that American air power operated within a different conceptual framework. The goal was not to win individual engagements, but to render engagement unnecessary. Reconnaissance platforms exemplified this philosophy by existing beyond practical reach. German analysts described this approach as strategically destabilizing, not because it provoked escalation, but because it exposed the limitations of defensive equilibrium. The balance of power was no longer determined solely by matching capabilities, but by redefining the parameters of contest itself. These realizations marked a deepening of the technical and doctrinal reassessment that had begun with earlier exposure to American aircraft. The encounter with strategic reconnaissance forced German specialists to confront the possibility that aerospace dominance was no longer bounded by conventional metrics. Instead, it was shaped by the ability to integrate technology, doctrine, and intelligence into systems that operated beyond existing frameworks. This understanding would continue to influence German and NATO aerospace planning throughout the Cold War. By the late 1950s and into the 1960s, German military analysts increasingly realized that evaluating American aircraft in isolation no longer produced meaningful conclusions. U.S. aerospace platforms were not designed to operate independently. They functioned as nodes within a vast, interconnected network that linked radar installations, early warning systems, command centers, and intelligence analysis units into a single operational framework. For German specialists accustomed to compartmentalized structures, this level of integration represented a profound conceptual shift. American radar networks formed a backbone of this system. Early warning installations stretching across North America and the Atlantic were integrated into centralized command structures that processed data in near real time. German observers studying NATO air defense exercises noted that radar information was not simply collected and relayed. It was filtered, prioritized, and transformed into actionable intelligence almost immediately. This compression of the decision-making cycle reduced uncertainty and increased responsiveness in ways that traditional command hierarchies struggled to replicate. The semi-automatic ground environment, known as SAGE, became a frequent reference point in German technical discussions. SAGE was not merely a radar network, it was an early example of computerized command and control at continental scale. German analysts recognized that SAGE fundamentally altered the relationship between detection and response. Aircraft, interception, missile deployment, and strategic alerts were coordinated through centralized computational systems that synthesized vast quantities of data. For engineers trained in environments where computation was localized and limited, the scale of this integration was striking. What impressed German specialists most was the redundancy built into American systems. Radar coverage overlapped, communication pathways were duplicated, command centers were designed to remain functional even under partial disruption. This resilience reflected an assumption of prolonged conflict rather than short, decisive engagements. German assessments repeatedly emphasized that American air defense systems appeared engineered not for perfection, but for continuity under stress. Failure was anticipated and absorbed rather than treated as catastrophic. This systemic approach reshaped the role of aircraft themselves. American fighters, bombers, and reconnaissance platforms were increasingly viewed as extensions of a larger sensing and decision-making apparatus. Their effectiveness depended less on pilot intuition alone and more on their integration with radar guidance, data links, and centralized command directives. German analysts noted that this reduced reliance on individual brilliance while increasing overall operational consistency. Air power became a collective function rather than an aggregation of individual performances. As German specialists delved deeper into American command and control doctrine, the distinction between technology and organization began to blur. The effectiveness of U.S. radar and intelligence systems could not be explained solely by hardware superiority. It was rooted in how information flowed through institutions. Data moved rapidly across organizational boundaries, reaching decision-makers with minimal distortion. This fluidity contrasted sharply with more rigid hierarchical models familiar to German and European military structures. German evaluations of joint NATO exercises highlighted how American forces leveraged information dominance to shape engagements before aircraft ever entered contested airspace. Threats were identified, categorized, and prioritized well in advance. Resources were allocated dynamically rather than pre-assigned rigidly. German analysts describe this approach as anticipatory rather than reactive. It allowed American forces to dictate tempo, forcing potential adversaries to respond within constrained windows of opportunity. This organizational intelligence extended beyond military structures. German observers noted close collaboration between American military planners, industrial contractors, and research institutions. Radar development, computing advancements, and operational doctrine evolved in parallel rather than sequentially. Feedback from exercises and deployments informed technological upgrades, which were rapidly incorporated into existing systems. This continuous loop accelerated adaptation and reduced the lag between innovation and implementation. One of the most unsettling realizations for German analysts was that American systems appeared comfortable with complexity. Rather than simplifying problems to fit existing structures, U.S. doctrine expanded structures to manage complexity directly. Large command centers staffed by multidisciplinary teams became normal. Decision-making authority was distributed across specialized roles, reducing bottlenecks. German reports emphasized that this organizational elasticity allowed American air defense systems to scale without collapsing under informational load. By the mid-1960s, German military discourse increasingly acknowledged that American technological advantage could not be countered through isolated improvements. Matching radar range or interceptor speed would not suffice. The challenge lay in replicating an entire ecosystem that fused technology, organization, and doctrine into a cohesive whole. This realization marked a turning point. Air power was no longer defined by aircraft alone, but by the invisible architecture that connected them. The shock was not emotional, but structural. German specialists understood that they were observing a model of warfare optimized for endurance, adaptability, and informational dominance. The implications extended far beyond aviation. They suggested that future conflicts would be decided less by singular feats of engineering and more by the ability to integrate systems at scale. For German analysts, the American approach represented not merely a technological lead, but a redefinition of how modern power was organized. By the late 1960s, German military and intelligence officials increasingly recognized that American technological dominance during the Cold War was inseparable from its intelligence architecture. Unlike traditional espionage models that emphasize secrecy through isolation, the United States operated an intelligence system that paradoxically combined extreme secrecy with selective transparency. For German observers, this hybrid model was both unfamiliar and deeply instructive. American intelligence did not function solely as a hidden apparatus operating behind closed doors. Instead, it was embedded across multiple layers of military planning, industrial research, and strategic communication. German analysts stationed within NATO structures observed that intelligence assessments flowed continuously between agencies, commands, and allied partners. Information was compartmentalized, but not immobilized. Each unit received precisely what it needed to function effectively within the broader system. This approach contrasted sharply with intelligence traditions rooted in rigid compartmentalization. German intelligence culture, shaped by both wartime experience and post-war caution, emphasized strict boundaries between collection, analysis, and operations. American systems, by comparison, appeared deliberately porous within controlled parameters. Analysts, engineers, and commanders interacted frequently, allowing intelligence insights to influence technical design and operational planning in near real time. German evaluations of American reconnaissance programs further underscored this difference. Platforms such as high-altitude reconnaissance aircraft were not treated merely as information-gathering tools, but as integral components of strategic signaling. Their existence, performance, and even partial capabilities were sometimes allowed to become known, shaping adversary perceptions. German observers noted that this selective disclosure functioned as a form of psychological and strategic pressure, complicating enemy planning without revealing operational vulnerabilities. Perhaps most striking was the scale at which American intelligence operated. Data collection extended across global networks of listening stations, aerial platforms, naval assets, and diplomatic channels. German specialists reviewing declassified material and Allied briefings described an intelligence environment characterized by volume as much as precision. The challenge was no longer acquiring information but filtering and interpreting it efficiently. American investments in data processing and analytical infrastructure reflected this reality. reinforcing the perception that intelligence superiority was as much organizational as it was technical. German intelligence officials, working alongside American counterparts, frequently commented on the role of trust within U.S. intelligence culture. While secrecy remained paramount, trust was extended selectively to individuals and institutions deemed reliable. This trust enabled faster decision-making and reduced friction between agencies. German analysts observed that once trust was established, information moved with remarkable speed, bypassing layers of bureaucratic hesitation common in more centralized systems. This dynamic became particularly evident in joint NATO intelligence operations. American officers often shared assessments, methodologies, and even analytical uncertainties with German partners. Such openness was not indiscriminate. It was calibrated. German reports emphasized that this approach fostered alignment without sacrificing control. By shaping how allies understood threats, the United States indirectly shaped their strategic responses, reinforcing its leadership position within the alliance. The American intelligence model also blurred the boundary between espionage and innovation. German observers noted close ties between intelligence agencies and technological research institutions. Information gathered through espionage informed research priorities, while technological breakthroughs expanded intelligence capabilities. This feedback loop accelerated development cycles and ensured that intelligence requirements remained aligned with emerging technologies. German assessments described this integration as a force multiplier that magnified the impact of individual advances. Equally significant was the American willingness to institutionalize lessons learned from intelligence failures. German analysts studying internal reviews and congressional oversight processes noted that setbacks were often documented, analyzed, and incorporated into reform efforts. This transparency within the system, though invisible externally, contributed to long-term resilience. Intelligence was treated not as an infallible authority, but as a dynamic discipline subject to continuous improvement. By the early 1970s, German intelligence discourse increasingly framed American power as informational rather than purely military. Aircraft, missiles, and bases mattered, but they were manifestations of a deeper structure rooted in intelligence integration. Espionage was not an isolated activity. It was a connective tissue binding strategy, technology, and diplomacy. For German specialists, the realization was sobering. Competing with American capabilities required more than technical parity. It demanded a transformation in how intelligence itself was conceived and employed. By the mid-1970s, German aerospace specialists within NATO began to encounter early evidence of American research into low observable aircraft technologies, a development that fundamentally challenged prevailing concepts of detection, air defense, and operational planning. Reports emerging from U.S. technical briefings, declassified studies, and Allied collaborative assessments indicated that the United States was actively exploring methods to reduce radar cross-section, control infrared signatures, and optimize aerodynamic design to evade existing detection networks. For German engineers, accustomed to evaluating aircraft primarily by speed, altitude, and maneuverability, these developments represented an entirely new domain of technical concern. The shock for German analysts was not simply the technical sophistication, but the holistic approach the Americans applied to stealth concepts. Low observable research was not limited to the airframe. It encompassed materials, science, engine placement, surface shaping, radar-absorbent coatings, and integrated operational doctrine. German reports emphasized that each element individually offered incremental advantages, but the cumulative effect produced a system that challenged the fundamental assumptions of radar detection and engagement. Engineers familiar with conventional design paradigms had to reconsider the relationship between visibility, vulnerability, and operational utility. What further impressed German observers was the iterative and classified nature of American experimentation. Test flights, wind tunnel experiments, and computational modeling were coordinated within secure research facilities, ensuring that technological advances remained shielded from adversarial observation while being continuously refined. Analysts noted that even when partial information became available, it was often ambiguous, requiring sophisticated extrapolation. German technical papers from the period described the difficulty of drawing concrete conclusions from fragmented intelligence, highlighting both the ingenuity and the strategic patience embedded in American programs. Importantly, these stealth concepts were not pursued in isolation. German assessments repeatedly noted that low observable research was closely linked to reconnaissance, strike planning, and broader aerospace system integration. Aircraft designed for minimal detectability were paired with intelligence platforms, electronic warfare assets, and command networks capable of exploiting the operational advantages afforded by reduced observation. The Germans recognized that the United States was not simply developing stealth aircraft as isolated tools, but as components of a larger doctrine of advantage, a system-level innovation that exceeded individual hardware improvements. The German realization of American low observable initiatives prompted a profound reassessment of technological parity and strategic forecasting. Analysts understood that conventional metrics, maximum speed, service ceiling, engine thrust were insufficient to capture operational advantage when detection itself became uncertain. German reports emphasized that stealth concepts represented a qualitative leap rather than a quantitative improvement, forcing a redefinition of defensive and offensive planning assumptions. This cognitive shift was further reinforced by American operational discipline. Stealth aircraft were designed not only to evade radar, but to exploit integrated intelligence networks that could direct missions with unprecedented precision. German engineers noted that even theoretical interception solutions were limited by the combination of signature reduction, strategic routing, and real-time intelligence updates. This contrasted sharply with historical paradigms in which engagement outcomes were largely predictable once aircraft were visually or electronically detected. Equally instructive was the American commitment to secrecy coupled with controlled information sharing. German specialists often received glimpses of technology, sometimes intentionally filtered to preserve operational advantage while providing allies sufficient context to plan collaborative operations. Analysts described this as a managed transparency, a delicate balance that maximized deterrence and minimized risk of compromise. For German observers, the sophistication of this approach combining technology, doctrine, and organizational control underscored the depth of American systemic superiority. By the late 1970s, the combined exposure to American low observable research, integrated reconnaissance, and command systems solidified a new perspective among German engineers. Technological advantage in the Cold War was increasingly defined by systems thinking rather than isolated capabilities. Aircraft, while impressive individually, derived their ultimate effectiveness from their integration within networks, intelligence streams, and operational doctrine. German reports conclude that achieving parity with American air power would require not only engineering but fundamental organizational and strategic adaptation, a realization that reshaped both aerospace thought and defense policy within NATO circles. These early encounters with stealth and integration planted seeds for later German research initiatives and influenced NATO planning for decades. The shock was intellectual rather than emotional. German specialists were forced to confront the limits of perception, the scale of organizational coordination, and the magnitude of technological foresight employed by the United States. It was a formative moment that defined how German engineers and military planners approached modern air power, setting the tone for both collaboration and strategic humility in the decades that followed. By the late 1970s and into the early 1980s, German aerospace engineers and military analysts were increasingly exposed to joint NATO exercises that highlighted the operational philosophy underpinning American air power. Unlike prior encounters that emphasized aircraft performance alone, these exercises revealed the efficiency of American planning, coordination, and logistical integration. German observers noted that U.S. forces could rapidly deploy units, synchronize multinational operations, and respond dynamically to unforeseen contingencies. Often without requiring extensive centralized directives, the exercises frequently involved a combination of strategic bombers, tactical fighters, reconnaissance platforms, and support aircraft, all orchestrated under a single operational command. German analysts were particularly impressed by the standardized procedures governing communications, maintenance, and mission planning. Every aircraft, from the F-4 Phantom to the B-52 Stratofortress, followed rigorous checklists and operational protocols that ensured predictable outcomes. This level of procedural discipline contrasted sharply with German experiences, where individual initiative often compensated for structural inefficiencies. A recurring observation among German reports was the speed at which American forces could translate intelligence into operational action. Data collected by reconnaissance platforms and radar networks were immediately processed, disseminated, and acted upon. Exercises demonstrated a compression of decision-making cycles that German planners found remarkable. It was not merely the technological sophistication of individual systems that impressed them, but the orchestration of multiple systems to function seamlessly under the pressures of simulated combat scenarios. These exercises also illuminated the strategic value of redundancy. American air power was built around the principle that no single failure could compromise an operation. Multiple bases, spare aircraft, overlapping radar coverage, and contingency plans allowed for resilience in the face of mechanical, logistical, or adversarial disruptions. German engineers concluded that such systemic robustness was as critical to American success as engine performance or avionics innovation. They recognized that technology and organization were interdependent, and that operational superiority was achieved through the careful calibration of both. Beyond technical and tactical observations, German specialists increasingly focused on the organizational culture that underpinned American operational effectiveness. During NATO briefings and joint exercises, it became apparent that decision-making was decentralized within well-defined parameters, enabling faster responses without sacrificing coherence. German analysts compared this to their own post-war structures, noting a heavier reliance on hierarchical control that slowed reaction times and constrained flexibility. Another striking feature was the integration of industry, academia, and military planning in American defense programs. Engineers observed that lessons learned from exercises were rapidly fed back into design and production cycles, allowing for continuous improvement of aircraft, electronics, and support systems. Maintenance protocols were standardized across units and nations, enabling interoperability even with allied forces that had previously operated with differing doctrines and equipment standards. The Germans were particularly impressed by how NATO exercises demonstrated combined arms operations at unprecedented scale. Coordination between air, land, and naval forces was managed through extensive planning, communication networks, and shared intelligence. Individual American units often operated as part of a broader system rather than as autonomous entities, a concept that contrasted with prior German expectations of tactical independence. Analysts concluded that operational efficiency was inseparable from systemic integration, a principle that would become central to German defense planning in the following decades. Additionally, German reports highlighted the psychological impact of American procedural rigor. The predictability of mission execution, coupled with redundancy and rapid problem-solving, created an impression of invulnerability, even when confronted with hypothetical, adversarial scenarios. While German specialists did not view this as insurmountable, they acknowledged that any attempt to compete technologically or operationally with the United States would require not only engineering advances, but profound organizational adaptation. By the early 1980s, it was clear to German analysts that the United States had effectively redefined operational standards for modern air power. Technology alone did not account for American dominance. It was the combination of precise engineering, integrated intelligence, and disciplined execution across multinational forces that produced strategic advantage. German specialists began to advocate for reforms that emphasized systems thinking, cross-functional coordination, and adaptive procedures, lessons learned from direct observation of American operational practice. By the early 1980s, German aerospace analysts increasingly turned their attention to the industrial foundations supporting American air power, recognizing that the operational advantages observed in exercises were inseparable from production, capacity, and innovation cycles. While German wartime engineering had produced groundbreaking aircraft such as the Messerschmitt Me-262 or the Heinkel He-162, these successes were often achieved at the cost of limited production numbers, dependency on specialized labor, and logistical constraints. In contrast, American aircraft programs of the Cold War exemplified a philosophy of scale, standardization, and continuous improvement. The F-4 Phantom II, as an illustrative example, was produced in thousands of units and deployed across multiple Allied air forces. German engineers noted that the United States achieved this through modular design principles, which allowed components to be manufactured simultaneously in separate facilities and assembled with consistent tolerances. This approach minimized bottlenecks and enabled rapid iteration of upgraded versions without halting production. The speed at which American programs introduced improvements, whether avionics, engine modifications, or weapons integration, stood in stark contrast to German post-war production, where iterative changes were slower and often hampered by smaller industrial infrastructure. Beyond quantity, the Germans observed the quality control measures embedded in American industrial processes. U.S. aerospace programs employed rigorous testing protocols at every stage, from prototype development to full-scale deployment. Defects were systematically identified and addressed without disrupting overall production time. German reports highlighted the sophistication of these procedures, emphasizing that American engineers treated production as an extension of design rather than a mere assembly task. This mindset ensured both consistency and adaptability, fostering confidence in the aircraft's performance, even under demanding operational conditions. Equally significant was the integration of research institutions, universities, and private contractors into the production pipeline. German specialists recognized that American innovation did not occur solely within military laboratories, it was distributed across multiple sectors, with continuous feedback loops linking operational experience, theoretical research, and industrial execution. This approach contrasted sharply with the more centralized German programs of the post-war period, where innovation often remained confined within a single laboratory or manufacturer, limiting speed of adaptation. German evaluations emphasized that the systemic integration of design, production, and testing in American aerospace programs had strategic implications far beyond the technical realm. By maintaining a consistent output of high-performance aircraft and rapidly implementing upgrades, the United States effectively reduced the operational window during which adversaries could challenge its capabilities. German analysts acknowledged that technological advantage was not static. It was reinforced continuously by an industrial ecosystem designed for resilience, speed, and adaptability. The Germans also noted that American programs allowed for risk-taking in a controlled environment. Prototypes could be deployed experimentally, data collected, and refinements incorporated into subsequent production batches without jeopardizing overall operational readiness. This approach was fundamentally different from German post-war experience, where smaller production runs and limited redundancy made experimentation inherently riskier. The U.S. model, in contrast, treated innovation as an ongoing, iterative process intimately linked to strategic objectives. By the mid-1980s, German specialists increasingly framed their assessments in terms of systemic lessons rather than isolated aircraft comparisons. The question was no longer which specific model outperformed another in speed, maneuverability, or radar capability. Instead, the focus shifted to how the United States leveraged its industrial base, research institutions, and organizational structure to maintain sustained technological superiority. German reports explicitly linked observed American advantages to a combination of scale, integration, and a culture of continuous improvement, a triad that explained much of the operational dominance witnessed in exercises and NATO collaborations. This perspective influenced German aerospace planning and industrial strategy, as policymakers and engineers sought to incorporate elements of American methodology into domestic programs. Emphasis was placed on modular design, standardized maintenance, and systematic feedback between operational use and technical refinement. Analysts concluded that the American approach represented a paradigm shift. Technological excellence was inseparable from production efficiency, organizational discipline, and institutional coordination. German engineers recognized that the full measure of American air power could only be understood through the lens of integrated systems, rather than individual hardware achievements alone. By the mid-1980s, German aerospace and military specialists were increasingly analyzing not just the hardware of American air power, but the operational doctrines that enabled its effectiveness. Observing U.S. Air Force and Navy practices during joint exercises and training missions, German analysts noted a profound divergence from traditional German paradigms, which had historically emphasized precision, discipline, and a strict hierarchy in command. American doctrine, in contrast, prioritized flexibility, decentralized decision-making, and rapid adaptation to real-time developments, reflecting a fundamental cultural and operational difference. German reports highlighted that American pilots were trained to operate with significant autonomy while remaining closely integrated into broader strategic objectives. This training emphasized not only technical mastery of aircraft, such as the F-15 Eagle, F-16 Fighting Falcon, and later variants of the F-4 Phantom, but also situational awareness, decision-making under uncertainty, and coordination with multi-domain assets. Unlike the more rigid, checklist-focused approach familiar to German officers, U.S. training encouraged pilots to anticipate contingencies and modify their tactics in response to dynamic threat environments, leveraging the full capabilities of command and control systems and intelligence networks. The German reaction to this approach was a mix of admiration and recalibration. Analysts recognized that operational flexibility was not synonymous with recklessness. Rather, it was a structured methodology for maximizing the effectiveness of integrated systems. While German forces valued precision and reliability, American doctrine demonstrated that outcomes could be enhanced when individual initiative was harmonized with systemic intelligence and organizational support. Exercises revealed that this method often produced faster, more adaptive responses in complex scenarios than traditional, tightly centralized command structures. Another aspect that drew German attention was the rigorous cross-training of American pilots. U.S. forces emphasized multi-role capabilities, ensuring that personnel could operate in various mission types from air superiority to tactical reconnaissance, electronic warfare, and joint strike operations often within the same aircraft or platform. German reports contrasted this with more specialized training, where pilots focused narrowly on one type of mission, limiting operational adaptability. This difference highlighted the American emphasis on creating versatile operators who could exploit the systemic advantages provided by integrated intelligence and communication networks. Beyond individual pilot proficiency, German specialists were struck by the integration of operational doctrine into broader system-level awareness. American training programs were designed to instill an understanding not only of one's own aircraft, but of the network of support assets, radar systems, command centers, and allied forces contributing to mission success. German reports consistently noted that U.S. pilots were trained to anticipate the actions of radar operators, reconnaissance teams, and electronic warfare units, effectively treating human and technological nodes as an interconnected system rather than discrete elements. Exercises conducted under NATO supervision revealed the practical effects of this approach. American units could coordinate complex maneuvers across multiple domains, exploiting information superiority to achieve objectives with high efficiency. German analysts observed that these operations required pilots and commanders to maintain a continuous mental model of the operational environment, dynamically integrating incoming intelligence, mission objectives, and the actions of allied forces. The cognitive demands were significant, but the results demonstrated a level of responsiveness and precision that challenged traditional German operational assumptions. German assessments emphasized that the shock lay not in individual technical capabilities, but in the doctrinal coherence and training philosophy that enabled those capabilities to be realized fully. While German engineers and officers possessed advanced knowledge and rigorous skill, the integration of doctrine, intelligence, and pilot initiative in American practice created a multiplier effect. This systemic approach allowed American air power to achieve strategic objectives consistently, even in scenarios where individual aircraft or personnel might be outnumbered or outperformed in isolation. By the late 1980s, German military discourse increasingly framed operational excellence as inseparable from organizational culture, training philosophy, and systemic integration. Aircraft, technology, and individual skill were necessary but insufficient conditions for superiority. It was the American ability to harmonize all elements human, technical, and institutional that produced the shock experienced by German specialists. These insights would go on to influence Bundeswehr doctrine, emphasizing interoperability, adaptability, and systems thinking as central components of modern air power. By the late 1980s, German analysts were increasingly confronted with the multifaceted nature of American technological advantage. Beyond aircraft, reconnaissance, and operational doctrine, U.S. forces had developed sophisticated electronic warfare (EW) capabilities that redefined the tactical and strategic environment. German specialists, long accustomed to evaluating performance metrics such as speed, range, or payload, now had to account for the invisible dimensions of conflict: radar jamming, signal deception, and integrated communications interference. American EW programs were structured not as isolated systems, but as components of a larger operational doctrine. Platforms such as the EA-6B Prowler and specialized EC-130 variants provided electronic support that directly enhanced strike missions, reconnaissance, and fleet coordination. German reports emphasized that these systems were capable of selectively disrupting adversary radar networks while preserving the integrity of friendly detection and communications. The precision and systemic integration of these capabilities were unprecedented, and German analysts recognized that traditional interception strategies were increasingly vulnerable to electronic countermeasures. Counterintelligence studies conducted by German units highlighted another dimension of the shock: the Americans' ability to conceal operational intentions while maintaining transparency with allies. German engineers noted that U.S. forces managed a delicate balance between secrecy and controlled information sharing. Allied partners, including West Germany, were provided with sufficient operational visibility to coordinate effectively, yet enough remained classified to prevent adversaries from predicting outcomes. This level of controlled dissemination contrasted with German post-war expectations, where secrecy often resulted in information silos and delayed operational responses. Moreover, German assessments emphasized that American EW capabilities were tightly coupled with intelligence operations. Electronic reconnaissance allowed U.S. planners to anticipate adversary movements and vulnerabilities, feeding directly into strike planning and defensive posture. German analysts repeatedly remarked that such integration amplified the impact of aircraft and systems that, when considered individually, might have seemed conventional. The combination of electronic warfare, real-time intelligence, and systemic integration produced operational advantages far beyond what was possible through hardware performance alone. German specialists also confronted the stark limitations of their own interception technology in light of American advancements. Traditional radar networks and interceptor aircraft, optimized for engagements against conventional targets, struggled to keep pace with platforms enhanced by stealth, electronic countermeasures, and integrated command guidance. Even when detection occurred, response windows were compressed by the speed and altitude of American aircraft, as well as by electronic disruptions intentionally introduced during operations. Reports from German technical evaluations repeatedly stressed that these limitations were systemic rather than isolated. While incremental improvements could increase radar sensitivity or aircraft performance, They could not overcome the combined effect of stealth design, EW suppression, and organizational coordination. Analysts recognized that achieving parity with American capabilities would require a holistic transformation encompassing sensor networks, pilot training, electronic countermeasure development, and operational doctrine. The Germans also observed that American doctrine exploited these asymmetries with remarkable foresight. Exercises demonstrated how EW platforms could suppress or manipulate radar signatures at precisely the moment when strike aircraft approached defended zones, effectively neutralizing the advantages of high-speed interceptors. German analysts noted that such operational layering created an environment in which interception became highly probabilistic rather than deterministic, a reality that necessitated fundamental reevaluation of air defense strategies. By the end of the 1980s, German specialists increasingly acknowledged that American technological superiority was inseparable from strategic systems thinking. Aircraft, EW platforms, radar networks, and intelligence pipelines operated as a cohesive entity designed to maximize operational effectiveness while minimizing vulnerability. German reports concluded that the United States had redefined the parameters of aerospace engagement. Success was determined less by individual performance and more by the orchestration of interdependent systems, a realization that continued to shape German planning and doctrine well into the post-Cold War era. As the Cold War drew toward its later stages, German analysts reflected comprehensively on the patterns that had emerged over decades of observing American air power, reconnaissance, and technological innovation. What had initially been a series of isolated surprises, the introduction of high-altitude reconnaissance aircraft, the SR-71 Blackbird, stealth research, and integrated electronic warfare had, over time, revealed a coherent and deliberate American approach. German reports emphasized that the shock was not simply in the capabilities themselves, but in the systemic thinking that unified technology, operational doctrine, intelligence, and industrial capacity into an almost seamless structure of advantage. German specialists consistently noted the difference in strategic culture. Where German post-war programs had often relied on specialized expertise and incremental innovation, American aerospace dominance was a product of integration across multiple domains. Aircraft were not evaluated solely for individual performance. Their effectiveness depended on how well they interfaced with radar networks, intelligence pipelines, electronic warfare systems, allied coordination, and command and control structures. This holistic approach challenged traditional German metrics for assessing air power, forcing analysts to develop new frameworks for understanding operational superiority. The shock extended beyond the technical into the organizational and American pilots, engineers, and intelligence officers operated within a culture that valued initiative within structured boundaries, decentralized decision-making, and adaptive responses to dynamic operational conditions. German observers frequently contrasted this with hierarchical post-war structures, where procedural fidelity often constrained flexibility. The result, they concluded, was a force multiplier that amplified technological advantages beyond what raw specifications alone could suggest. Perhaps most revealing to German analysts was the realization that American superiority was technological innovation informed doctrine. Doctrine informed training. Training informed industrial priorities, and industrial capacity facilitated further technological experimentation. Each element supported the others in a feedback loop that produced sustained advantage. German reports stressed that catching up required more than copying aircraft designs. It demanded a systemic transformation in how air power, industrial production, and intelligence were conceived and applied. In their final assessments, German specialists synthesized a series of strategic lessons. First, technological innovation alone was insufficient. It required integration with intelligence, doctrine, and operational planning. Second, production scale and industrial coordination were as decisive as aircraft performance. Third, pilot training and operational flexibility could multiply the effectiveness of even established technology. Finally, the management of information through controlled transparency, operational secrecy, and integrated intelligence was a critical determinant of strategic advantage. These insights had profound implications for German aerospace and defense policy. Bundeswehr planners increasingly prioritized interoperability within NATO, modular design in aircraft production, enhanced pilot training, emphasizing systems thinking, and integration of intelligence into operational decisions. While Germany did not seek to replicate American capabilities directly, the lessons derived from decades of observation influenced domestic innovation, doctrinal evolution, and strategic planning well into the post-Cold War era. From a historical perspective, the German reaction underscores a broader truth about technological and operational superiority. It is not merely a function of hardware, but of the coherence between technology, organization, and strategy. American air power during the Cold War exemplified this principle, demonstrating how an integrated approach could consistently outperform technically competent but isolated systems. The legacy of this realization shaped both European military thought and the broader understanding of modern air power, illustrating the enduring value of systemic advantage over singular technological achievement. In the end, the German experience was one of repeated surprise, critical reassessment, and eventual adaptation. Observing American innovation forced German specialists to confront the limits of their own assumptions, rethink operational doctrine, and embrace the necessity of integration across multiple domains. The Cold War, in this respect, was as much a contest of ideas and organizational foresight as it was of aircraft, missiles, and radar. For American observers and historians, these reactions provide compelling evidence of the systemic and enduring superiority of U.S. aerospace strategy throughout the period.